everyone. So my name is Giulia Cinquegrana. I'm a first year PhD student working with Amanda Kraukas and Alexander Hager at Monash and Lisa Cooley and Meredith Joyce externally. So the focus of my PhD project is to study the most metal-rich stars in the universe. I'm really interested in how the physics of metal-rich stars alters the chemical contributions that they make to the interstellar medium. So I'm looking mostly at the low and intermediate mass range and focusing next on the border of intermediate to massive stars. So we can study this by looking at theoretical models of the last phase of evolution for these guys, which is the asymptotic giant branch and the superasymptotic giant branch, where we can measure the changes in their chemical contributions as a function of metallicity. So what do I mean by the most metal rich? Well, our yields are the first to extend to metallicities beyond metal mass fractions of 0.04. So that's about twice solar, up to metal mass fractions of 10%. So just to define what I mean by yields, when we generate yields, we're measuring the composition and the quantity of the mass that is expelled from stars and returned to the surrounding interstellar medium. So for low and intermediate mass stars, this is by stellar winds that erode the outer envelope. For massive stars, also by supernovae. So this allows us to track what metals are coming from which kinds of stars or events. What's the point of studying the most metal-rich stars? Well, for starters, we simply know that stars with metallicities greater than solar exist. For example, the metal-rich bulge of spiral galaxies, such as the Milky Way, giant ellipticals such as M49, and we know of many metal-rich open clusters. However, these stars are completely left out of galactic chemical evolution simulations, or their yields are just extrapolated from solar. So as I said before, our yields that we're about to publish are the first to extend beyond metallicities of 0.04. So apart from just bridging this missing metallicity gap, one of the questions that we're asking is there a threshold for which single stars stop contributing primary isotope nucleosynthesis to the interstellar medium? So as a reminder, primary nucleosynthesis is the production of nuclei from primordial hydrogen. For example, in the case of nitrogen, that would mean we have hydrogen to helium burning, helium to carbon burning, and then later on the giant branches, hydrogen burning on that fresh carbon. Secondary nitrogen production is going to be hydrogen burning on carbon that is already present in the initial stellar gas from a previous generation. Why do we care about this? Well, primary production is going to increase the global metallicity of the stellar gas. Secondary is just going to rearrange the ingredients. Okay, so the first stop, I've been working with metal-rich low and intermediate mass AGBs. This is the last phase of evolution for low and intermediates, where there are two phases to the AGB, the early AGB and the thermally pulsing phase. The thermally pulsing AGB is the best place to look for variances in nucleosynthetic patterns, purely because there is so much going on there. So AGBs, thermally pulsing AGB stars, as a reminder, have a degenerate carbon-oxygen core with two intermittent hydrogen and helium burning shells. So we want to know what the nucleosynthesis looks like here. We've got hydrogen shell burning, helium shell burning. We can also have heavy element production in the region between the two shells, which we call the intershell region, via the slow neutron capture process. So all of these processes happen inside the central region of the star. The secret ingredient then is the mixing process known as the third dredge up. So this is when the outer convective envelope can extend inwards in mass and mix the products from the intershell region out to the surface of the star. So without third dredge up, none of these burning products will be contributed back to the interstellar medium. They're going to remain locked inside the white dwarf remnant. So I've just said that this is the third dredge up. As a quick reminder, there are two mixing events prior to the thermally pulsing AGB. That's the first dredge up on the red giant branch, and for intermediates, the second dredge up on the early AGB. The major difference between the first two and the third is that the first and the second only mix the products of hydrogen burning to the envelope. Third dredge up is the first time that we're seeing helium burning products brought up to the surface. Also, first and second dredge ups only happen once. Third dredge up can occur after each thermal pulse, which depending on mass and metallicity can be tens to thousands of events. So there's one more process in AGB stars that doesn't rely on third dredge up events. If the temperatures are hot enough at the base of the convective envelope, usually in intermediate mass stars, there can be hydrogen burning at the base of the envelope. So what we want to know is what happens to these processes as we increase our metallicity well beyond solar up to metal mass fractions of 10%. Well, the first thing that we notice is as metallicity increases, the mass threshold for third dredge-up increases. So what I've got plotted here is the initial mass on the y-axis and increasing metallicity on the x-axis. So what we're trying to show is that all these really important mixing and nucleosynthesis all have pretty strong mass dependencies. So for third dredge-up to occur, we need this blue hashed region where at metallicities of 0.04, we can see that we get third dredge-up events at 3.5 solar masses. But at 0.07, at 0.07, we don't get third dredge-up until about 5.5 solar masses. So on top of that, the mixing as metallicity increases becomes really inefficient. So this is a plot of the mixing efficiency lambda as a function of time, where we use thermal pulses as a proxy for time. So a lambda value of 1 is the most efficient mixing. That means that all the burning products that have been created during the previous interpulse period are scooped up by the envelope and mixed up to the surface. If lambda is 0, that means that none of those products have been moved into the envelope and the core just retains that growth. So we can clearly see that there's a downward pattern that ensues with increasing metallicity. So for metal-rich stars, this means that we see virtually no products of hydrogen or helium shell burning in the envelopes. So just to emphasize, these processes do still occur, but the products are going to remain locked inside the white dwarf remnant. Even at the lowest end of our metallicity range, this really significantly impacts heavy element production by the slow neutron capture process. So even if their dredge-up operates at 4 solar masses for metallicities of 0.04, it's really inefficient until about 6 solar masses. However, optimal S-process nucleosynthesis occurs in the lower mass regime. So by the time we actually get to see the products up in the envelope at 6 solar masses, we see very little production of these elements. So lastly, the process of burning at the base of the envelope is also not immune. Because metal-rich stars are puffier and less dense, they have cooler temperatures in their gas, especially at the border of the hydrogen shell and convective envelope. So this is just showing the maximum temperature at this location as a function of initial mass. So blue shaded region is temperature sufficient for partial hydrogen burning. They're peachy colored regions for full hydrogen burning. We can see that as metallicity, at solar metallicity, we have we have temperatures sufficient for full hydrogen burning at this location, whereas by the time we get up to 0.10, we only have very mild temperatures for a couple of the most massive models. Okay, so you can see now where my question comes in. By the time we get to the most extreme of our metallicity range, there's no third dredge up, very little burning at the base of the envelope. So what does this leave us with then? Well, any nucleosynthesis that comes out of these stars is a direct consequence of their initial metal content. So for hydrogen burning by the C cycle, we know that the ingredients have to be conserved. If we start off with more burning ingredients, then we're going to make more burning products. So if we look at the nitrogen-14 yields, for example, even though the 0.10 model doesn't undergo third dredge up or very much hot bottom burning, it has the highest nitrogen-14 yields because that initial material is brought to the surface during the first and the second dredge up events prior to the thermally pulsing AGB. So our very metal-rich stars are going to contribute yields that are predominantly comprised of secondary hydrogen burning products. So this means at the extreme end of our metallicity range, they are not contributing fresh metals back to the universe. Thank you.
Nice talk, Giulia. So Anshu is asking, out of curiosity, fractionally, how many stars are metal-rich in galaxy, like Milky Way?
I don't think it's really, I don't know the quantitative fraction, but if we're looking at a picture of the Milky Way, anything within that bulge is going to be solar metallicity or metal rich. Anything outside that is going to be more metal poor. So I'm not sure of the number quantity of that, but yeah.
Yeah. So question is on slide. Thank you very much, Giulia.